The last talk of this session before the panel is mine, so Photonic integration from the data center. And I want to acknowledge a lot of collaborators from a bunch of different companies that we work with, as well as a bunch of collaborators at UCSB. And of course, funding support from DARPA and ARPA-E in particular. So how do we reduce energy consumption, increase capacity in data centers? We've heard over and over again about co-packaging, and that's certainly key, right? You have to eliminate the 50 ohm terminations and drive the modulators directly capacitively, not with the 50 ohm load. That's essential to get the power consumption down. Second thing is increased integration. So obviously higher data rates, baud rates, as Robert showed, more complex modulation, as Dan showed, and more wavelengths and ports in parallel. And that starts to take one to large numbers of devices integrated together. And particularly DWDM is key, I think, to getting to these rates, and as you've seen in the previous talks. So, 100 devices today and more in the future. So here's one effort we did at higher levels of integration. So this was a network on chip. It was 2.5 terabits. We had 8 banks of a total of 64 lasers and modulators and detectors, and integrated together. And again, just like Robert's talk did, shows the value of integrating lasers on chip, because otherwise it becomes painful of all these different wavelengths presenting, integrated or not integrated, but connected by fiber. And we have AWGs and so forth. So that was an early effort, but as one gets more and more wavelengths, it becomes necessary to look at other sources. And so we have a program that Gordon Keeler is funding called QUIL. It's a DARPA Pipes project, and with a bunch of other partners, in particular Analog and SUNY and Sienna, Intel, HPE. But now we're looking at 40 wavelengths and lots of integration on chip. In this case, the wavelength source doesn't come from multiple separate lasers, but rather from one mode lock laser generating the 40 wavelengths. And that's a good way to go. We'll talk about different ways to get there. But we can hit the half a picojoule per bit with this architecture, and that's what we're aggressively working on now. The laser source, as I mentioned, is mode lock, and this is some earlier results. This is not the right spacing for pipes, but this is a 20 gigahertz spacing, and we're able to get 64 wavelengths across here, and enough power in each line that we could transmit data, 32 gigabaud PAM4, and get up to 4 terabytes. So that's, I think, a really nice way to go to get these high levels that we're talking about, in the not so distant future. A second way is to do comb generation. And we've been looking a lot at optical injection locking. And again, when you take a CW laser pumping one of these high-Q resonators and you injection lock, then you get this comb that is very quiet. It's single soliton comb is quiet. And the optical injection locking means you get this turnkey operation. You get solitons every time you do it. And they're very stable. You don't need to adjust the power. And that's shown here. And what we've seen is that, particularly in the most recent archive paper, that each of those lines can be very quiet. We've seen down to 3 hertz Lorentzian line width on each of those lines. In this case, we don't need PDH loops or anything else to lock. It's the optical injection locking that of this laser to the high Q resonator that matters. And we're up to 60 dB noise reduction. The slide here doesn't show up, but the archive paper does. And so I think this is a really good way to go to get lots of wavelengths integrated together. That still takes quite a bit of power. It's typically 100 milliwatt sorts of numbers, or at least tens of milliwatts. And one way to get beyond that is to use a different material than silica or silicon nitride. In particular, we're looking at using aluminum gallium arsenide, because it's 1,000 times more nonlinear than silica and 100 times more nonlinear than silicon nitride. And consequently, you can live with a lot lower power. And so this shows here you can generate combs, these nonlinear combs, with just 36 microwatts of power. And so that starts to become something you could integrate onto a chip and not require a lot of power. And again, when you lock these to high Q resonators also on the same chip, then you get this large reduction of linewidths down to just a few hertz. And then you don't need DSPs in the coherent system so as to lock it. And that's Dan Blumenthal's point in particular. So the next step beyond increased integration is obviously coherent. And again, Raj talked about that being more power efficient at 1.6 terabits per second. And again, we need a higher spectral efficiency, eliminate the DSP. And so we've been working on using the fact that silicon and silicon nitride waveguides have very low losses. And consequently, the line which you can get are very small. So today we're about 120 hertz, a little better than this. We have the next generation we think is 40 hertz Lorentzian line width. And when we lock that to a resonator, the integrated line width that NIST shows is about 30 hertz today. So this slide shows the progression we've gone through over the last 7 years down these line widths. But again, what we're utilizing is the fact that silicon, silicon oxide, silicon nitride have very low losses, and that gives you very narrow line with lasers. And so this is all the work in the world, and lots of these other points here are from other groups around the world, but many groups around the world are seeing these line widths down to just below kilohertz. And I think we'll soon see numbers dramatically better than that. So that's what's really exciting. The thing we're working on is shown here, where you integrate the laser with the silicon nitride waveguide. And in this case, there's a gradient in the waveguide. And this is a collaboration with Morton Photonics. And the nice thing is that the thermal optic coefficient, is 7 times smaller than silicon. So consequently, as you can see here, as you change temperature, the laser doesn't change wavelength very much. And I think we can do even better than this, but this kind of eliminates the need for CWDM, because if you make the AWG and the laser out of silicon nitride, then there really isn't much wavelength change with temperature. So I think this sort of structure will become ubiquitous. And Gordon Keeler is funding a Lumos program, and a key part of that is having silicon nitride waveguides integrated with lasers on chip. And I think technologies like this then become widely available. So to summarize, I think significant reductions in energy consumption are possible. We can certainly, I think, hit 10th picojoule per bit. The key things are integration with CMOS. You have to flip chip the electronics onto the optics. That's where eliminate all the 50 ohm lines, eliminate equalization, eliminate clock recovery. Laser integration's key, as Robert said, reduce losses from coupling the laser onto the waveguides, and the ability to have more robust, more complex schemes, lots of different wavelengths available. DWDM, I think, is key. Probably by either Modoc lasers or turnkey soliton combs. And that partly depends on what the spacing is. If it's 100 gigahertz or less, I think Modoc lasers are probably by far the best way. 100 gigahertz or more, it's then sort of the nonlinear combs. And I think gallium arsenide works well. And then moving to coherent. So I want to thank my students, particularly for doing all the work that goes on at UCSB. And I'll be glad to take a couple questions, and then we'll move into the panel session. So I can't see the slides. So if there's any questions from the panelists, you can shout them out. And
yeah, there aren't any new questions on the Q&A, John, so far.
Okay. All right. Well, let's move on to the panel.